Mm. Okay, so hello everyone. Uh, uh, so yeah. So I wrote you an email maybe half an hour ago about this schedule and possible options. So please think about this, and maybe we'll discuss either the next time or by email. Uh, and uh, I want to ask, do you have any questions about the last time or about the problems? Oh. Uh, if not, let us continue the computation that we were doing the last time. So this computation was the computation of the grand function for the wave equation. Uh, so So a short reminder that we knew that this grand function in the momentum space was minus 1 over omega squared minus k squared. And we had to take the Fourier transform of it. And we did it as follows. So j of kx maybe tr better to write like this was equal to so it depends only on the absolute value of r due to rotational symmetry, and it can be checked also explicitly. And it is given by this integral. So it was first integral in d omega. So maybe I'll skip all these prefactors like 2 pi and everything else, so they can be recovered, but I don't want to compute them explicitly because it's not so important. So, or maybe I'll keep them for some time. So. And this integral goes over this contour. So this is k minus k, and k is the absolute value of k. And the integral goes like this. So the contour is this one. So it equals to Heaviside theta times this integral and this was so the some factor of phi here, and this was e2 minus I omega t plus I oh, I kt plus I k kr minus E2 plus IKT plus IKR over 2k. And then we could change the sign of the second exponential by changing k to minus k, or by changing the angle. So anyway, we can do like this. Oh, maybe let us keep it like this for some time. But then we switched to hyperspheric coordinates, and this integral was transformed to some. Let us write just some constant CD times integral k d minus 2 dk. So this is for this integral. And the omega from 0 to infinity. It's kind of radial integral. And also there is an integral in one angle, in angle between k and r. The one angle which enters this expression. And we computed the measure in this integral, and it turns out that it is a sine of theta to power d minus 2. D theta. And the expression that we have here is now e2 minus I k t plus I k r sine theta minus, so actually it is sine, but maybe it is easier to write it as a difference of two exponentials. Maybe better to write it like this. So this is, and we also computed this integral for d equals to 1. It was the last time. So are there any questions about this formula, or everyone remembers it, or can quickly cover this computation? That's fine, right? So we have already computed this integral for d equals to 3. So for d equals to 3, it equals, so this grand function t and r equals to up to some coefficient, which I don't want to write, or maybe I can write it here. Pi r, and here it is a delta function of t of t minus r. So it is this expression. And now let us compute it for d equals to 2. Actually, it turns out a little bit more complicated, because for d equals to 3, we just computed the center angle integral, and the remaining integral was just an integral for the delta function. But yeah, thank you. Of course. So now d equals to 2. So in principle it looks simpler, but actually it is a little bit more complicated because for example, in the previous case, I think we could compute this integral first in r, then in theta, and it would give a kind of the same answer. But if we try to integrate this integral first in theta and then in r, then we will get Azier's Bessel function, and it is not so nice. So let us first compute the integral in R. So d equals to 2. So this green function is so it is I c d times integral from 0 to infinity decay from 0 to pi in actually it is not 2 pi but 2 pi because in the so in the n-dimensional case it is kind of the first variable, and in the two-dimensional case it is the first and the last variable. So so it is from 0 to pi d theta, and the integral itself is e to minus ik t minus r sine of theta minus e to the ik t minus r sine of theta. So if we try to integrate this in k, then we see that it is integral is not so well convergent. In some, this function does not go to 1 at infinity. Or it does not go to 0. But as always, we can say that we can a little bit modify its Fourier image by something like e to minus epsilon k, and it will not matter if compute convolutions of the green function with some smooth enough sources, because they go to 0 at infinity. So this modification of green function at infinity will not change the answer, and like a solution and a limit when epsilon goes to 0 will coincide with just the value at epsilon equals to 0. So we can always use this trick. And if we do this, then this integral equals to integral from 0 to 2 pi d theta. And it is 1 over epsilon plus I k t minus r sine of theta. Minus 1 over epsilon minus ik t minus r cosine of theta. And of course there is heaviside theta of t everywhere. Mm. Hmm? Uh, because like a integral of e to minus epsilon k dk equals to 1 over epsilon. It is just positive. So it's how to remember all the signs. So uh, mm, uh, so this tells us that what is written here is actually the principal value of 1 over k t minus r cosine of theta. So it is precisely the definition, because if the pole of this expression lies on this interval from 0 to 2 pi, then we should move a little bit up, a little bit down by adding plus minus I epsilon, and I take 1/2 of this of these expressions. So uh, this is the definition of the principal value. So it is I theta side of t, this principal value integral from 0 to 2 pi d theta to d theta over I k t minus r cosine of theta. Uh, yes. Oh, yes. Sorry. Yes. Like this. Hmm? Uh, But in this case, let us actually compute this constant, because, well, at least here we can compute a explicit value. So originally we had 2 pi. Here we had this 1/2. So um, this 1/2 so maybe this is minus I, because we had mm, no, it is I. It is fine, because we had two minuses. So this gives us I over 2. Here we still have 2 pi, and so here it is I over 2. Mm, and it's I over 2. Okay. Mm. Yes, so now we have this integral, and uh, there are now there are several options. One option is to say that oh, how to do this better. Uh, Let us switch. So it is 1 over 2 pi also. the theta over 2 pi, because there was 1 over 2 pi here, so and here I'm the same. Let us switch in this integral from integration in theta to integration in such a variable z equals to e to the I theta. This variable goes. So this variable lies in the unit circle. So this can be written as 1 over 2 pi I integral around 0, integral over the circle when absolute value of z equals to 1, dz over z. T minus r minus r over 2 z plus z inverse. Or equivalently, can be written as minus 1 over 2 pi minus minus 2 over r. Such kind of expression. And now the question is, where are the poles of this expression? If absolute value of r is greater than absolute value of t, so let us postpone this computation and consider the two options. One option is absolute value. No, just they are both positive. So when t is so r is greater than t, then what we see that there is so equation cosine of theta equals to t over r has two solutions. Some theta star and what else? Theta star plus pi. Not plus pi. Theta star minus theta star. Or in terms of z variable, it means some z star and 1 over z star. And so for this z variable, these points lie on the unit circle. So I have a picture like this. So grab this unit circle, this z plane, and there are these poles somewhere. because it is a variable which is e to the I theta. So this theta star is just some angle. It's some real number. If r is greater than t, so it is something which is less than 1, and there is some explicit angle theta for which this cosine equals to this ratio. Right? If it is greater than 1, then we only have complex solutions of this equation. So, so there are these poles at the unit circle, and there are only poles of this expression. So if you now use this principal value prescription, and so we can write, maybe the simplest way is to say that this integral equals, this principal value integral equals to 1/2 of integral for absolute value of z a little bit smaller than 1 plus absolute value of z a little bit bigger than 1 plus this one. On this one. But I know the question. What is the value of this integral? Like, if you look at this function, can you say this immediately? Yes. Yes. Right, because there are no singularities with this function inside. And what is the value of this integral? It is one way to compute this, but another way, well, of course, you can compute this explicitly, but simpler way is to say that we can equivalently not shrink this contour to 0, but instead send it to infinity. And we see that this, there is no pole at infinity because it is dz over z squared. So integral z over z squared over some absolute value of z equals to r equals to 0. We can change, we can, for example, perform change of variables, z to 1 over z, and so maybe let us write it here. So if we say that z equals to 1 over w, then our integral will have a form like d minus dw over w squared over w minus 2 minus 2t over r w minus 1 plus 1, and it will equal to integral minus dw over w 1 minus 2t over r w plus w squared. So it is clear that this function written in the inverse in W inverse has no pole around W equals to 0, or which is the same as Z equals to infinity, and so this integral is also 0. So the residue is always coefficient in front of 1 over z, so or if we want to take care of orientation, it will be coefficient minus coefficient in front of 1 over z. But the point is that the computation of this integral is that z equals to some finite value, or z at infinity takes care about 1 over z coefficient. So this function, better to say this one form, does not help over at infinity. So this integral is also zero for this reason. So is it fine? Yes, they as always, yeah, the waves propagate with speed equal to the speed of light, or speed of sound. So. This gain function should always vanish outside this cone. So, since we are able to compute this integral, we see that in this case, and this gain function equals to 0. Okay, but now let us consider another case. So, on the second case, 2. If r is less than t. In this case, this equation does not have real solutions, and it means that one of these poles is inside this unit circle, and another one is outside, because of Wiert's theorem that product of two poles, like two values of z at pole is equal to 1. So if r is less than t, let us find the roots of this equation. T squared, so the star squared minus 2t over r, z star plus 1 equals to 0. Z star equals to 2t over r plus minus t over r plus minus square root of t squared over r squared minus 1. And due to this restriction, this square root is positive. So let us call it like the star 1, 2. And let us choose that z star, which is inside the unit circle. So the star is equal to better not to introduce this extra notation. Better to introduce it, probably. So this root is definitely smaller than the other one, and it is less than one, and another one is with plus. So our integral now can be written as uh, what? As 1 over 2 pi I minus 2 over r uh, integral over absolute value of z equals to 1 dz over z minus z star 1 z minus z star 2. Mm, so this integral equals to the residue at z star 1. So it is minus 2 over r uh, 1 over z star 1 minus z star 2. And I forgot heaviside theta. Okay, so we have this expression, and now let us substitute a explicit value of this z stars. So the star 2 is, of course, t over r plus squared over squared minus 1. So let us substitute this and get 2 over r beside theta of t over square root of t squared over r squared minus 1. Like, and this 2 will be cancelled, so it equals to root of t squared minus r squared. So it's the end of the computation. Right? Uh, it is well-defined generalized function because if we want to integrate, for example, let us take some fixed value of r. This integral f of t in dt over what let us imagine that we use this grand function to compute to find the solution of our wave equation utt minus u minus what xx minus u y equals to some f of t x and y. So if you now want to find this u of t, x, and y, we use this gain function and write the integral in sorry, I also forgot to write that there is this Heaviside theta, which tells that this expression vanishes uh, when t is less than r. So it is Heaviside theta of t minus r. Mm. Let's think. And actually, since r is always positive, we can remove one of this. So can we do this? Well, of course we can. And in principle, I wrote this Heaviside theta here, but we can easily remove this because when t equals to r and r is positive, then Heaviside Heaviside theta of t is of course positive. So we can remove this one. So it is this expression. Uh, so if we now want to compute this solution, then we should integrate over dt prime, dx prime, dy prime, u of f of t prime, x prime, y prime, and here the green function. Heaviside theta of t minus t prime minus square root of x minus x prime squared plus y minus y prime squared divided by square root of t minus t prime squared minus x minus x prime squared minus y minus y prime squared. So if you now compute this integral in t prime, then what is the singularity? So t prime integral. So it is like integral from so it can be so it's some quadratic polynomial with some roots. So it can be written as so we have some function of t prime, and we integrate f of t prime over some t prime minus a times t prime minus b. Actually, like this. So we compute this integral from more or less minus infinity to b, for example. If b is less than a, so suppose b is less than a, then this integral is well defined because we can say that it is some integral from minus infinity to point C, dt prime, f of t prime over the square root of t prime minus a, t prime minus b. So it is convergent. Plus, when the integral from c to b, some f tilde of t prime, where we included t prime, square root of t prime minus a, over square root of t prime minus b, dt prime. So it is it can be integrated by parts, for example. Let's c to b. Tilde of t prime d square root of t prime minus b. So well, we can integrate it and get something finite plus some definitely convergent integral. But actually, it was just a complicated way to say that if we have a singularity less strong than 1 over t, then an integral to the singularity is convergent. Because okay, we can just check this, integrate by parts once, and that's all. And by the way, concerning such integrals, I'm not sure if there is a precise relation. Oh, by the way, are there any questions about this formula? So about such integrals. There is such a thing called fractional derivative, which is very similar to what is written here. So we think let us consider the following. So let us suppose that f of t goes to 0 fast enough when t goes to minus infinity. Oh, I will not write this assumption explicitly, but let us say that we define the following object: d alpha of t, which is integral from minus infinity to d alpha f of t, integral from minus infinity to t, dt prime over t minus t prime minus t to power alpha f of t prime. And another yeah. And this alpha should be, let us say that it is from 0 to 1. In this case, this integral is convergent. and so f of t should be of order 1 over t when t goes to minus infinity. So we can define such objects. And now let us consider the composition of two such derivatives, d alpha, d1 minus alpha, and d alpha, acting on f of t. So if we want to do this, we should write that now this t is some new variable, and we should add another integral of this kind. So it is integral from minus infinity to t, some d t with 2 primes over t prime minus over t2 primes minus t power 1 minus alpha. Integral from minus infinity to t with 2 primes dt prime over t prime minus t 2 primes f of t prime. So we have this integral which may look a bit scary, but it is actually not so bad, because we can try to change the order of integration. So let us draw the picture with this integration variables. So we have integral in t prime and integral in t with 2 primes. And we see that integral in t2 primes goes from minus infinity to t. So here this restriction, and everything which is above this line should be excluded. This is one restriction. Another restriction, that integral in t prime should go from minus infinity to t with 2 primes. So let us draw this line. So if we fix some t2 primes, we fix some line, we know that integration in t prime goes from here to this line. This is t equals to t prime equals to t with 2 primes. So this integral goes over this domain, this triangle which goes to infinity. So is there any question about this? So and so now we can change the order of integration. This integral from minus infinity to t minus infinity to t prime now will go like this. So first let us see the order of let us check the range of integration in t prime. The maximum possible value of t prime is t. So this integral goes from minus infinity to t dt prime. And for given value of t prime, the range of integration in t2 primes is from t to is from t prime to t. So it is an integral from t prime to t with 2 primes. And now the expression under the integral. This expression is uh, 1 over t prime minus t with 2 primes to power alpha times t 2 primes minus t to 1 minus alpha times f of t prime. So this integral from t prime to t dt 2 primes is some function of mm, with some k of t of t and t prime. And now let us compute this kernel. So we see it. Maybe the simplest way to compute it, well, in principle, we can shift this integration variables, look at the Jacobian, and so on. But the simplest way to do this is the following. We can notice that this is a function which is defined in the complex plane, and it is single valued when t prime is large enough, because this these two powers, alpha and 1 minus alpha, compensate each other. And if we and the behavior of this function is 1 over t, and this expression k of t prime is the integral, like so. So there is a branch cut from t prime to t, and if we go around this branch cut, then we see that this function will be multiplied by e to the 2 pi alpha. So we can write that this expression can be written like so. So this expression can be written like this. So let us choose this contour in this way. So this can be written as 1 over 1 minus e to the e2 minus 2 pi I e2 plus 2 pi I alpha times a integral around this contour C of this expression, dt with 2 primes over t prime minus t 2 primes to alpha 1 t 2 primes minus t to 1 minus alpha. And then this contour, this integral in C can be shrunk to infinity, and the asymptotics of this function at infinity is so we should look at the coefficient in front of 1 over t. So it will be equal to e to the like 2 pi I, e to the 2 pi I, or e to the pi I alpha, because of this minus sign here, over 1 minus e to the 2 pi I alpha. And also this integral was clockwise, so there is also a minus sign. So finally, it gives 2 pi. It gives pi over sine of pi alpha. And the miracle is that this integral does not depend neither on t nor on t prime. And this fact that it is independent from t and t prime could be checked by just a usual change of variables. But it is some nice way to compute this. In principle, this is some beta integral. It could be computed as a value of a beta function, and actually it's one of possible ways to compute something for these beta functions. So yes, because we just look at the asymptotics when t to primes goes to infinity. Here it is minus t to primes to power alpha, and here is t to primes to power 1 minus alpha. So overall power is 1, and we should be careful about the coefficient and about the direction of integration. So this integral is just a constant, and you see that it equals to pi over sine of pi alpha, integral from minus infinity to t f of t prime. Actually, we can compute the composition of different d's, like d alpha and d beta. But the point here is that this composition of derivatives, like so in this way we obtain that d alpha times d 1 minus alpha is pi over sine of pi alpha. Let us call this integral as inverse to derivative of f, like d inverse. So in particular, if you take 1 over square root of pi d 1/2 and takes square of it, then we will get just just an indefinite integral of f. So but now, once we have this, once we can take square root of integration, we can compose this integration with an arbitrary number of derivatives. So, for example, so what can I erase? Probably I can erase the beginning of this computation. So you're asking about the order. It's absolutely the same. Uh, so you can just change alpha to 1 minus alpha, and this sign will not change. So it is equivalent. So, well, so using this, we can define. For example, d k minus 1/2 of f equals by definition to the integral from minus infinity to t uh, uh, f k of t prime over uh, square root of t minus t prime dt prime. No, t minus t prime, because it should be positive. Uh, oh, sir, probably I made a mistake here. Yes, sorry, it should be t prime minus t. No. No, oh, it should be t minus t prime. And so it should be change everywhere. So that this expression is positive on the interval from t prime to t. So sorry, so this one should be correct. Yes, so now we can define this this expression, and naively we could try to rewrite this as we can try to integrate this expression by part, and formally we can do this because we can write that it is integral from minus infinity to plus infinity, like theta of t minus t prime over square root of t minus t prime f k of t prime dt prime. So formally it equals to minus 1 to power k, integral from minus infinity to plus infinity, dk over dt prime case of theta of t minus t prime over square root of t minus t prime. F of t prime dt prime. And we can think that it is some normal function, but actually it is a generalized function, because we should somehow differentiate this discontinuous Heaviside theta, and this derivative of heaviside theta will somehow interact with singularity coming from the square root. So if you write something like this, it is perfectly defined as a generalized function, but maybe it is even hard to write some epsilon sequence which converges to this function, but maybe it's possible. I did not try. So in this case, it should be defined as delta prime, such that integral with this, that any integral with such a kernel should be understood as a integration by parts when all these derivatives are put to a function into this probe function, and after this, the integral becomes convergent and can be computed. So I'm actually telling this because it's not only funny, but because something like this appears in the higher dimensions for this green function. So, another way to think about this, if we don't want to this integration in t prime, we can think that we first take this fractional derivative of f, like took d minus 1/2 of f, and after this started to act with k derivatives. And here is the same problem, because, for example, we have this integral from minus infinity to t. F of t prime over square root of t minus t prime, t prime. Let us take, for example, a derivative in t, d over dt. So this is a well-defined object. But if you start taking this derivative, then we should first take a derivative in the integration in the upper integration limit. So it is f of t prime over square root of t minus t prime. And then we should differentiate this expression under the integral minus 1/2 integral from minus infinity to t f of t prime dt prime over t minus t prime to power 3/2. And we see that there is a problem here because it goes to infinity. So we should put here something like t minus epsilon. And also the integral is divergent, so we should also put t minus epsilon here. So this is why such expressions should be understood only as generalized functions. And actually they're somehow similar to derivatives of a delta function, but just these are fractional derivatives. And let me change the exponent. So we see that these operators now become non-local. So it was expected for the integral to be a non-local expression, but it turns out that these half derivatives are also non-local operators which know about the function from minus infinity to a given time. So, and it is similar to this green function. So, are there any questions? No. And now let me tell about the arbitrary dimension. So we already seen that odd and even dimensions are different. So let us first consider the case when d equals to 2 plus 2n. So in this case, we have an integral from 0 to infinity. Well, let us first notice the following thing, that if we take the operator of this kind, d over dt squared minus d over dr squared, if we take this operator and act with it on e to plus minus I k t minus r cosine theta, then it gives what? It gives a minus k squared in this first part. And the second part gives k squared cosine theta times e to plus minus I k t minus r cosine theta. Yeah, thank you. So it equals to minus k squared sine squared theta times this exponential. So using this observation, we can now write this integral for arbitrary d in terms of integral for smaller d. So we can use it to shift dimension by 2. So because of this, green function in dimension d plus 2 equals to some coefficient. So it depends on t and r. It equals to some coefficient which I don't want to compute times this operator d over d squared over dt squared minus d over dr squared, acting on green function of d, t, and r. Since we computed this for d equals to 3 and d equals to 2, then it's enough to compute it for arbitrary value of d. So if now d equals 3 plus 2n, then green function will be given by d squared over d t squared like this. In principle, it can be rewritten up to some coefficient like d t plus dt minus acting on a delta function of power n, delta function of t plus t minus. And I think it can be written as nth delta function of t plus times t minus, like nth delta function of of t squared minus r squared. Because like t plus is t plus r, t minus is t minus r. And the same for d equals to 2 plus 2n. So now it is equal to d t plus d t minus. Now I'm writing that this is the same as to put here. So I can write it as t plus r, like 2 over t plus r, because anyway t equals to r. Since this delta function, and then I can move this under the delta function. So there is an identity that delta of t minus r over r equals delta of t minus r over t plus r 2 equals to 2 delta of t squared minus r squared. I think because it is a delta function, it is a delta of alpha x equals to 1 over alpha delta of x. So, uh, because it is d over dt squared minus d over dr squared, so it is like we can write it as a sum and difference of the separators, and so this is precisely what we did for two-dimensional wave equation. So, is it fine? So this green function is this nth derivative of more or less t plus t minus. So it is 1 over t squared minus r squared to yes. Mm-hmm. Yes, thank you. But actually, these formulas are more or less useless because anyway it is some generalized function, and we will need to define it somehow. So it is just to see how it looks like approximately. So here we should write something like this, because it's those are some equalities for generalized functions, and we should say what is the precise meaning of it. it is something not very nice, and in any case, if you really want to compute something for some explicitly given a function, we should either compute it in the coordinate space or uh, take care about this derivative operator to move it to our source function. So I'm just writing some formulas, for example, to show its asymptotics, to show that it actually depends only on the interval, on the invariant combination, t squared minus r squared. But I don't think that these formulas, except for d equals to 2 and d equals to 3, are practically useful. Mm. But so, are there any questions? Oh, I think so. For Laplace equation, we could just look at the asymptotics at zero. So let me think. So for this even cases, or for this odd cases, we can just consider the problem with a static source and compute asymptotics of this given function around zero and compare it with the answer for corresponding Laplace operator with corresponding Coulomb's law in this dimension. Yes. And so and this and, so let me think. Hmm. So we will need to take care about this derivatives in any case, because if you substitute a delta functional source, it may be complicated to compute this. Maybe the easiest way is just to compute this integral carefully. No, but but the main message is that these gain functions of the wave equation are much more complicated than for Laplace than for Poisson equation, and that their behavior depends on dimension of the space-time in such a way. Because, for example, uh, if we uh, so so let us consider a point like source at the origin which emits some waves for this wave equation. So it is r equals to 0, and so it means that we are solving equation like utt minus Laplacian of u equals to and let us put here some kind of no charge maybe. So let us say that there is some force depending on time. So it means that we are solving this equation on the right hand side given by some function f of t, a delta of r. So it is at the origin. And now let us compare the answer for t equals for d equals to 2 and d equals to 3. So d equals to 3. U of t and r equals to the integral in dt prime d3 r prime f of t prime delta of r prime, which is on the right hand side of the equation, times the green function delta of t minus t prime or t minus t prime minus r minus r prime over r minus r prime. So if you now for pi, if you now integrate this integral in r prime, then it will be just put to 0 because of the delta function. So it will be given by the integral dt in t prime maybe sorry, let me do this computation for arbitrary d. So no, I don't want to erase this. So it is f of t prime delta of t minus t prime minus absolute value of r over 4 pi absolute value of r. So, and if you now compute this integral in t prime, then it gives just f of t prime f of t minus absolute value of r, length of r, over 4 pi 4 pi r. So it is actually very similar to a solution of 1 plus 1 dimensional wave equation with some boundary condition, and it's actually the same problem because I showed you at some moment that radially symmetric Laplace equation in 3D can be written as like as Laplace equation in 1D. Laplace operator and radial part of Laplace operator in 3D can be obtained by conjugation from Laplace operator on a half line, and it should be conjugated precisely by the absolute value of R. And this is the solution of a problem on a half line with some initial condition. So here, this left-hand side, delta function left-hand side is translated into the initial condition for the wave equation on half line. So it can be derived in some alternative way without this Fourier transform. And here the same picture. So if we say that f of t is something like this, some combination of pulses like this. Then for some fixed value of t, and for some for some fixed value of t, this u of t and r will look like this: u of t r, and this is r. It will look like so we have this big pulse, which was the last one. Then it is some smaller pulse, which is here, and here is even smaller pulse, which is here, because it is multiplied by 1 over r. But the point is that if we stay at some point and listen to the sound, we will hear some separated pulses and silence between them. But let us now look at d equals to 2. So, well, are there any questions about this? Yes, yes. So we have kind of radio waves which are emitted by this point at the origin. And by the way, there is also another way to compute these gain functions in different dimensions. For example, if you don't want to compute the angle integrals like this one, if it looks too complicated, we can say that Laplace wave equation in 3D is the same as wave equation in wave equation in 2D is the same as a wave equation in 3D, but without dependence on, for example, z coordinate. So we can say that from 3 to 2, to d equals to 2. So if you want to do this, we can just substitute a function f in the right hand side, which is a function of like f of t x y z is just a function of t x and y. And in this case, one integration in the green function, like will be the same for all functions. So we see that when we need to integrate even in a variable z, then this argument does not depend on it. So it will lead to the following: that green function in 3D t x y or in 2D will equal x y will equal to the integral from minus infinity to plus infinity of g3 of t x and y z dz. So maybe it is better to do it as an exercise to try to compute this integral explicitly. and to see that answer. But now let us just consider d equals to 2. So here as before, this first integral in r prime can be computed, and we will be left with integral dt prime of this green function. So it is Heaviside theta of t minus t prime minus r. Better write like this over yes, I've already integrated this. Okay, I can write it without skipping the steps. So it's integral dt prime dr prime, and here what is it? Is a Heaviside theta of t minus t prime minus r prime over square root of t minus t prime squared minus r minus r prime squared. So the square root times f of t delta of r prime, f of t prime delta of r prime. So now integrating r prime, and the remaining integral will look like integral dt prime theta of t minus t prime minus r, that's absolute value of r, square root of t minus t prime squared minus absolute value of r squared f of t prime. So it is integral in t prime from minus infinity to t minus absolute value of r. dt prime f of t prime over square root of t minus t prime squared minus absolute value of r squared. So here it is. So we see that if f of t prime was 0 on this integral, then the answer is still 0. But so it means that there is so there is one sharp front of this way. It cannot move faster than the speed of sound or speed of light, but it has infinite tail behind, because even if f is 0 for a long time, this integral still has some contribution. So asymptotically, so here we saw that if you look at some specific point, then at some moment the value of u becomes 0, but here it is 0 all the time. So I have this difference between different dimensions. So are there any questions about on this? So let me show another application of this green function. So maybe. And by the way, this integration is not literally the same as this fractional derivative, but it looks quite similar. So I think it's some different generalized function, but with similar square root asymptotics. Maybe. Whereas this. So here we placed some source at the origin and made it time dependent. But there is another possible problem when we imagine that we want to compute electromagnetic field generated by a moving particle. And so in this case, we should say that f of t and r equals to some charge times delta function of r minus r of t. So r of t is some given function. Right. So if you want to do this, then u of t and r equals to what? It equals to the integral delta of t minus t prime minus r minus r prime over 4 pi r minus r prime times this delta function. So now again, as before, we can compute this integral in r prime. It will put r prime equal to r of t prime. So it was integral d r prime and dt prime. So it now becomes delta of t minus t prime minus r minus r of t prime divided by 4 pi r minus r of t prime. So naively, one would like to put t prime just equal to t, because well, we have t minus t prime, but the point is that this term also depends on t prime. So we should use this formula with the derivative of the delta function, or with the derivative of the argument of the delta function, like delta of f of x equals to 1 over f prime, value of f prime, delta delta of x minus actually sum x minus x alpha sum over zeros. So if it's suppose that there is only one zero, mm, if a solution of this equation has only one zero, then it can be written as mm, 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 what, so let us say that mm, mm, this t prime mm, so mm, maybe I will run out of notations. Mm, so let us say that we introduce the variable t star, which is defined by this equation: t minus t star minus r minus r of t star equals to 0. So it will be defined by this equation, and then this integral equals to 1 over 4 pi r minus r of t star star and times derivative of the delta function. 1 over maybe better to change sign here. We can write it like, well, I'll not change it here, but it is just a derivative d over dt star, t star minus t star plus this one minus r of and here we should put t anti-prime equals to t star. So derivative of the first term is 1, and if we want to compute derivative of the second term, and then what it is, d over dt prime of absolute value of r of t star minus r is r minus r, and here we have scalar product, derivative of r times r of t star minus r of t prime minus r. So if you substitute this here, then we see the following expression. Mm. So like this. So it can be written if we denote it as a difference, then it equals to 1 over 4 pi r, like delta r, minus delta r times v. Uh, And if you think a little bit about this expression, then you can realize that, for example, if you substitute a particle which moves with a constant speed, that then this expression is invariant combinations, scalar product of a radius vector to this particle times force speed of this particle. So. Hmm? Uh, mm, what do you mean? Mhm. Mm. Mm. Okay. So, yeah, so there is such a formula. By the way, there is some tricky point that if you consider, yes. So actually, if we want to consider the actual electrodynamics, we need to solve the same equation, but also with speed inserted here for the vector potential, and the formula will be absolutely the same. Uh, the point about this is that uh, this expression can be obtained even without this computation, because we know that our wave equation is invariant under rotation group in 1 plus 3 dimensions, so we could just solve this problem for point where source at 0. No, sorry. If this particle moves with constant speed, then we can obtain this solution from solution of the wave equation with a static delta functional source. We can just perform rotation in this 1 plus 3 dimensional space and get this expression. Or we can write originally invariant combination of this for velocity and for vector, and then perform this transformation. So. There's some tricky point that if we consider a motion with a speed greater than speed of light or of sound, we will see again this Markov cone or Cherenkov cone, in the sense that this equation delta of something equals to 0 will have solutions only for points. So if it is some velocity v which is greater than 1, then this equation will have solutions only in this cone, and this formula will work only there. Otherwise, the solution will be 0. And well, for velocity less than 1, this solution just describes a little bit modified Coulomb law. In this case, it will cause the radiation. So this particle will lose its energy. And so to get some correct predictions, it's not enough to consider this ideal situation of the wave equation. We should add some non-trivial dependence of some dispersion law and non-trivial dependence of frequency on the wave vector, and so it is a more complicated problem. But there is such a phenomenon which can be seen even from this gain function. Okay, so thanks for your attention, and see you on Thursday.